a coffee roaster, and they've got a demand of 14,400. I think it's pounds. Is that it? Yeah, pounds of coffee per year, and then they have the option of buying a roaster for $35,000. Let's see. The setup is they sell the coffee at $7 a pound, but it costs them $3 a pound to do it right now because they don't have a roaster. They just buy it from a supplier. If they buy the roaster, it's going to cost them $1.60 per pound, but they can't sell it all for $7 a pound. They can only sell $7 a pound up to the $14,400 or 14,400 pounds they sell now. Anything above that, they can only sell at $2.90 a pound because I guess it's they're not selling to the Starbucks customers. They're selling to local stores or something. They got to make a profit. So they're asking they're looking at different scenarios of demand, and I don't want to dwell on it, but they've got a low, medium, and high demand. They've got an equal probability, and so they're looking at it in a couple of different ways. One of the things that, if you want to look at this Excel and download it, they do a nice job. I mean, of making. If you look, their little model. And I was like, whoa, that's look at this, it's pretty complex. So if you want a nice, learn a little bit of playing with the Excel, it's kind of nice. But basically, what they're dealing with all of those min and max and stuff is they're dealing with the transition at the 14,400 pounds as you go. What you have to switch price, and you have to look at which scenario are you doing, the medium or the low demand. But you can see the point I want to make is they calculated the break-even point between no roaster and buying the roaster, and it's at 25,000 pounds. So one point that they make with that is, well, you already said in your setup, and part of the setup of the problem was you can only sell 14,400 pounds a year in your coffee shop. For whatever reason, they didn't give a reason. So this is beyond that. So at least when you're considering the no roaster case, none of these demand scenarios change what you're making. With the no roaster, you're only selling 14,400 pounds. You're making $4 a pound because you're selling it for $7 and it costs you $3. So you notice that regardless of the demand, the no roaster income was the same because you're already set up. You're already going. You can't go anywhere else with it. And then they look at buying the roaster, paying $35,000 up there, and then different demands, whether it's 18,000 pounds, 25 or 30, and different levels of income based on that demand. And again, that's just calculating, $4 an hour for the first 14,400 pounds, $4 a pound, and then $30 a pound for the ones above it. And so you look at it, you can kind of see it in a table, but perhaps it might be better to see it in a diagram. So they've got that. So you buy a roaster or not? No. Then you're just down here, and you make the same. Even though the demand was 25,000, you could only meet 14,400. That's all you could meet. You made the same. So your expected value is a no-brainer. There's only one option: sell it all and here. But if you do buy it, you had 3 different demand levels. Each of them are equally probable. You had different profits that you calculated, and the product of that and that and that, and sum them up, you get an expected value of 57,840. So, the conclusion is, well, do you want to buy it? Well, I would say absolutely not. Look, 2 of your demand levels, it's worse, right? The low and the medium. Only the high demand level did you actually do better. And even if you look at your expected value, it's only $240 more than what you're doing already, and you had to commit $35,000. I mean, God, I'd rather stick that in the bank, earn a little interest. I don't have the risk of the roaster. I'm not getting in the roasting business. So that's my conclusion on this. And so, you can see how this kind of analysis would be an easy way to now argue this point with someone. Don't do this. It's a bad idea. You're hanging everything on this one demand, and that's risky. Let me do the little supplemental part, and then we'll talk about discrete event simulation. I wish more here. Let's see. All right, so this is a supplement. It's shorter. It's going to just do advanced waiting line, and I'll go through it quickly because it is short. And basically what they're doing, they're taking those formulas, the Poisson formula, and those how much time you spent in waiting or in the whole system, and they've expanded them. How did they expand them? Let's see. They expanded them by looking at a couple of different ways. The one way we just had was you had a single line and a single process. That picture, remember? But you don't have to have that. You might have multiple lines in one process, split and a process here, or you might have single line and multiple phases following each other. So if you have these different setups, can you calculate the amount of time in there, the amount of inventory, those kind of things? And the answer is yes, and I won't dwell on it. But if you assume a probability for your waiting time, as the Poisson distribution again, and maybe you have different arrivals. You got the Poisson distribution, and maybe your different service times. You either have the exponential, like we did in our example in the previous view graphs, or maybe you have a constant service time. Either you can still do the math and calculate it, and then there's other things that could influence it, which we will talk about in a minute. So let's look. So in their book, you've got this giant table. What is it? It's got the number of units, the average number waiting, average number of units in the system, average time spent waiting, average time spent in the system. This first row is the one we just did in class, the formulas for each of those. This row is for when you have multiple. That's what the big, this row. This row is the multiple. That's what the big M is. This is for, so this one is, the second row is for Poisson arrivals and a constant service time. So you can see the only difference is a little 2 shows up in here. And then the multiple line one looks somewhat more complex. But the point is, in this section, you've got the tools to calculate a couple of different scenarios. The average time waiting and the average queue size, those kind of things. So then that's what they do. For an example, they take Luck's car wash, okay? And Luck is a high school student, they say, and he's got a crew that can wash cars, and he can wash a car with his crew in 6 minutes. And they arrive once every 8 minutes. So first, they want to, and this is, it's an exponential arrival, so it's not saying it's fixed at 6 minutes, or I mean, the washing time is fixed at 6 minutes. It's a distribution. It's an exponential distribution. It can take them 5 minutes. It can take them 7 minutes. But the lambda, the mu in the exponential distribution is 10 cars per hour. 60 minutes divided by 6 minutes. The arrival rate, the lambda in the Poisson distribution, is 60 divided by 8. So now they say, well, let's just calculate all his performance capacity calculations. You know, the number of cars waiting, the number in the system, the average time spent waiting, and the average time he spends in the system. So just plug and chug. Here you're putting your 10 in, here you're putting your 7.5, and figure it out, okay? Average number of cars waiting, 2.5, 2.25, 3 in the system. You spend 18 minutes waiting, and you spend 24 minutes in the system. Now you would say, okay, the natural thing is let's improve, or let's change our system. So the first thing that Luck wants to do is go buy himself an automated washer. You know, one of those you sit in and wash. So he's going to take this right here, and instead of being an exponential distribution, now it's constant. So you can see what he's doing from a business sense. He's reducing variability. You know, the variability in this thing is what messes you up a bit. So if I buy the automatic thing where everybody gets in there and I push the button and it's going to take 6 minutes, you know, regardless. Now, you know, you're leaving out the fact that it might break or they might have a hard time getting the big SUV in there or something. We're not talking about that. Just you know, making a simple model first. So here, nothing changed in respect to these the size of these numbers, but the formula's changed, right? Because now this is a Poisson distribution. This is fixed. So we used that formula in the second row with the 2 in it. And so you know what it did? It just cut those times in half. That's all it did. It was the same formula. Cut it in half. Yeah, cut that one in half, and then these it did not cut in half because remember they had a sum in there. There was that one cut in half. This one was not. That one and that one cut in half. That and that had a formula. But you can see what it did. You had fewer cars waiting. You had fewer cars in the system, the average time spent waiting went down, the average time spent in the system went down. So if he can afford and somehow justify buying the automated system, good, right? He improved his process. Now the last decision he might make was, well, instead of buying this automated thing and having to worry about maintenance and all, let's add another crew. Let's add 2 crews. Instead of my 3 guys washing cars, let's get 6 and have a second crew. And let's make the same calculations. So let's see. He does, yeah. So they're more complex. So yeah, he's got to do them one at a time. There's the, first you evaluate this parameter, and then you plug it in. This is for the cars in the system, average waiting time. I was hoping they summarized. No, they didn't. But you see it improved. Yeah, 1 minute, 7 minutes was the time in the system. Number of cars waiting went down to 0.1. So adding a second crew was the best thing to do. And so again, you can analytically evaluate all of these. So that's a good little section. Now, could you do this a different way? And this is where they point to simulation modeling is where I want to go. Yeah, you can. And let me show you how a simulation model looks in the last few minutes here. Or you could do Monte Carlo, not Monte Carlo simulation. So here, they use this SimQuick, I use XtendSim. Let me get that one for you. Because I got a little presentation I made when I taught this before on this. All right, so a simulation model, a simulation modeling tool is also called a discrete event simulation. Just a tiny bit of motivation. You'll think about systems, right? Now this is a vibration equation. It's an ordinary differential equation, right? I got just one little variable. Well, that should have been over there. Sorry about that. Look at heat transfer. This is a partial differential equation, right? I got the partial derivatives, partial derivative here. And then manufacturing throughput doesn't look anything like that, right? You got there it is, there's my picture. Yeah, you got products come in, they pile up, you wait in the queue, you assemble, you wait in the queue, you continue. It's neither one of these. Things go on for a little while, and then you got a big period of time where nothing happens, and while you're working on something, in the model nothing happens. So the first discrete event model I worked on, I got time, my watch is good, was I was working actually with my brother. My brother has his own company. He's an expert witness, and I work with him a lot of times on some of his projects. And one of the ones we had this big bulldozer going down a hill, and its brakes failed. It was on an 18-wheeler, and the brakes failed. It got to the bottom and hit a house. And if you're going about 100 miles an hour with a 20-ton bulldozer, that's a lot of energy. It's like a bomb. And so there was, needless to say, there was some litigation associated with that. And so we built a simulation of it going downhill. And I didn't even realize at the time that it was making a discrete event simulation because things didn't happen for a while. You just go down the hill until something happens. What happens? Well, the brake heats up, you have to shift gears, the transmission or engine explodes, something like that. So you could go, I didn't have to do like a different, a finite difference simulation or a time simulation. I didn't have to go a little 1,000th of a second time step. I could just go wait till the next thing happened. And that's the way a discrete event simulation works. Things come in, and sometimes things don't happen for 10 minutes because you're working on something, the state of the system didn't change. So you can simulate months or years real quick. Whereas if I'm writing a simple time simulation like you do with the differential equation, you've got a time step of 0.0001 seconds to keep it stable. How are you going to simulate a year's worth of manufacturing? I mean, okay, it's just marching through time. Sometime next month you'll have the simulation done if you run it on the Ornell supercomputer. And so that's why they came up with these things. And there's different ways to do discrete event simulation. You can just write it in general language. There are C++ and C libraries you can buy. Go for it. Good luck. That's what you want to do if you're making one huge. There's specific simulation languages that are set up to do these things that you want to do. Because you can see in manufacturing, you've got things. You've got activities. You've got queues. You've got failures, mean time between failures. You've got a specific set of things you'd like to do. So there are specific simulation languages. They're good. They're nice. Or there's simulation tools that are graphical tools. These are nice. These are easy. You can build a simulation in them, literally in if you're good at it in an hour, and the simulation's not so complex. Now it may take a long time if you got a complex simulation. And there's more. This is the one UT uses. in your department, this is one I use, there's about 20 more. There's a bunch of choices, depending on how much you want to pay, what you want to do. You can also do them in a spreadsheet, and I've got some examples in Excel for you I'll show real quick. So what does the simulation modeling tool look like? This is the extend that I use. Here's your arrivals. Remember we had Poisson distribution, we had exponential distribution. It's just a box you pulled in out of a library, you click on it, in fact I'll show you that in the next slide, and you set up the distribution. So if you wanted that arrival rate of 3, well, you just plug 3 in the little box, turn it on, and make the little balls come out. And the little balls can be made into boxes or cars or people. If you want to animate it, you can do that. They go to what? A line, a queue, you know, they wait in the line. They go to what next? Something, you do something, right? You wash the cars, you wait, you make the part, you move the part to the next machine, and when they're done, they go out. Okay. Now this is a dumb one, right? It's just one activity. Things show up, things sit, things get worked on, things leave. You can have a million activities, you know, hundreds of activities. You can tie them all together, you can have hundreds of queues. And you just build this by connecting the blocks and clicking it, filling it in. For example, this is an activity. Oh yeah, look, I did an exponential distribution. The mean was 1, that's an arrival of 1 minute or hour, depending on your time you set it up. And you can put a maximum number of units you can make, and they'll just come out. And they'll come out from a distribution. You know, they won't come out 1, 1, 1. They'll come out of 0.9, 1.1, and they'll stack up. The activity, the queue, you can say what happens. You can have a maximum. You can have reneging. You can require things to show up before you can get out of the queue, like boxes or parts or tools. Let's see. Here's the activity. Yeah, it's got a delay. This could come from a distribution. It could be a statistical distribution. It can need people. It could fail. It could spit the thing out when it fails, or it could quit. There's all sorts of things you can see actually you do on these tabs. You can have cost, you can animate it, you can have failures, you can tie that in, and then your results come out. Big graphs you can show. Here's the things coming out. Here's a utilization. You have the machine. You can see there's different lengths of time between when they come out. Yeah, because there was different lengths of time when they arrived and different service times. So these are nice little tools. So yeah, here's a bigger model, right? I come in, I did one thing, did a second thing, 1, 2, 3, 4, 5 things, 4 things, and come out. You can count them, you can just get nice tools. So if you want to build a model of some process, and you want to do it quick, and you want to add some really unusual logic, you can pick one of these tools. If you wind up wanting to do it and you need some help, I can help you on it. You can get Extend as a student for like $50. Now your model size is limited. Yeah, it's limited to like 200 blocks. If you get more than that, you can buy the whole thing. And the whole thing is not that bad. It's like $1,000, more than you want to spend as a student. But certainly not, Y12 has copies. And so does the lab. And so does UT, actually. We could get it through there if you wanted to build it. But the $50 version's fine. Here's just a random sampling of results. But these are great tools. You can make a histogram. I mean, you can go on ad infinitum. It's a good, very powerful thing to do to model the types of systems you deal with in here. Systems that have random things going on, that have queues and lines and logical behavior that isn't a heat transfer problem, a distributed system like that. And that being said, too, if you don't have the $50, you can do it in Excel. Okay, so I've got 2 of them in Excel, just to show you real quick. So this is so this what I built is sort of the same one you just saw at Extend. You have 4 activities and 4 queues. So I've got things coming in, I've got a queue that stacks up, things take amount of time, and then you got the total time out here. And how did I figure this out? You can look, it's online. Let me blow one of them up. I've got at the top, I've got an average time that it takes to do something, a standard deviation, and I just sample a random distribution. And you'll learn how to do this in statistics. And then I do the same thing for this one, and this one, and this one, and then you just add them all up. And so you can see, because I'm sampling from a random distribution, you would think it takes 5, 4, 3, I got 5 activities. Oh, yeah, 4, right? You got 1, 2, 3, 4. Oh, that's, yeah. 1, 2, 4, 5. Yeah, so I've got, must not have used one of them. But anyway, you can see how the time is very different. So now you can get a statistics. like I said, you could make a histogram, whatever. Yeah, and then I've got one more model I did. I added just a different variability. I had variability on the mean, and so if you didn't have much variability on the mean, it's real tight, like I talked about. If you had a lot of variability on the mean, the histogram spreads out. So you learn a little bit about your system. And you can build these things in Excel, and this also is a Monte Carlo simulation. See how I got 100 and some replications, so I can build a histogram, or like I said, I could get a 95% confidence interval on those times. I could really start understanding my system, and it wasn't that hard to build. Now, why would I use it? Why would I ever buy XtendSim? Well, this doesn't have a ton of the logic in it, right? This has got a Q and a weight, and a Q and a weight. I don't have any reneging, I don't have resources, I don't have the rich plethora of things you could do with a simulation model. So Excel is extremely limited, but again, just like the calculations, you got the hand calculations you can do as a first step, Excel that you can do as a second step, and then a simulation model could be a real model, a real good model. Like I said, Y12 built a model of the UPF in XtendSim. It's a huge model, hundreds of thousands of blocks that calculates throughput for all the different products we have, and all it's amazing what you can do with the tool. That didn't get built in a week, that's for darn sure. But anything that you guys might entertain for your capstones, you could build a good model in a week with these tools, and be coming up with results, throughputs, utilization. I mean, it just a click of a button, it calculates these things and plots them for you. You can get a lot of information fast, and a lot of understanding of your system for $50. Yeah. So that's my spiel on capacity, and when the logic gets hard, you can go to a simulation modeling tool. But if not, you've got some hand calculations and those kind of things. So I thought this was a fun chapter, although it was truly all over the map. Statistics, your econ, simulation modeling, you name it. But, it's there. And the last thing, you guys asked me about a book. I did the statistics book that I would like to use is available in paperback. A couple of you guys were asking.
$20 on Amazon.
$20 on Amazon, right? It's on. If you don't know where to find it, it's there. It's online. I put it on the blackboard for you. Yeah, it's $20 on Amazon, and that's the one. As long as it's cool with Carla, actually here, that's the one I'll choose because I've used it before. I love the book. It doesn't have the mathematical rigor, but as far as statistics, apply statistics, and using statistics, it's a gem. And the pictures, man, the nice colored illustrated pictures. I feel like once you go through that, you really got a handle on applied statistics, which to me, that's what you want. You don't want to be statisticians. You don't want to be deriving, the extreme value statistical distribution. I don't think. And if you do, change majors, Really, I mean, that's cool. Statistics is great. It's great, but, there it is. So if you want to get a head start on, paperback, $20. And there's also, it has a student value edition that I talked about too, so I suspect Carl will go for it. I hope so, because it's a good book. You'll feel like you own statistics. I did. I've got several statistics books, and after I went through this one, I was like, nah, I can talk statistics now, at least to at the level you need to make the decisions you want. But yeah, that's it. So that's on Blackboard if you forget, because I would forget. Levine. And see, it's what, the 7th edition. Most of the errors are gone. It's a beautiful book. I got some books I like, some I hate, That one I like. We'll get excited if we learn out of that one. Food's still not here, is it? Oh, well, get out there and get it. Golly, tell me shut up. Gotta be hungry. There we are. It's supposed to be a nice weekend, guys.
Good.
No, good weather. It's supposed to be. Good.
Yeah. All right.
I tell you, once I learned discrete event simulation, I'd use it all the time.
So if you want the template already. No, just Jay.
To me, it's very difficult to answer a throughput question without the discrete event tools. Because you're hamstrung. You either got these hand calculations that assume distributions and assume a few things are going on, or you do Excel, but that's not the way. Once you go this far into a process, it's not the way processes work. You got people getting sick. You got people